Thanks for filming again.
Okay. So we're going to heat our crucible on a triangle over this flame. And the touchiest part of this is to get enough oxygen into there so that it has enough oxygen to react with without...
Do you want me to turn on the fan?
That probably is a good plan.
Do we need to mention like a triangle and everything, or just that the crucible?
The crucible is heated, it'll do fine. But just so you guys know what the thing is called, we've got a crucible and a triangle. So, anyone read The Crucible ever, the book?
Oh, yeah.
Yeah. This will quickly demonstrate, I don't want shards in my tea if it breaks. This will quickly demonstrate exactly what a crucible is, because it'll glow like blazing red hot. Oh, and also we don't want to burn up the other part of our experiment.
Can we look at this straight on? Or
Yes, you won't be able to see it very well. So what's happening in there is our metal is going to react with the oxygen in the air and form a new compound, this powdery white stuff, magnesium oxide. We know how much the magnesium weighed before. Will you expect the product to weigh more or less?
could you repeat the question?
We know our metal weighed 0.81 grams. It's going to react with oxygen to form magnesium oxide. Do you think the magnesium oxide will weigh more or less than 0.81 grams?
More.
More. Why?
Because oxygen was added to the magnesium.
Right.
And they form chemical bonds, and therefore.
Perfect. So, once we make magnesium oxide, that's MgO, is that going to be an ionic compound or a covalent compound?
Ionic.
Ionic, how do you know?
Because magnesium is a metal.
Perfect. Okay, so this takes a while, and I'll occasionally fan it a little bit with the lid to try to get extra oxygen in there so that it uses up oxygen. If anyone thinks the fumes are awful, we can absolutely open the window or anything we need to do there. Crucibles are meant to be heated to a very high temperature. Let's hope our little guy is a good one. Alright, so we can do some math while we're chewing our gum, and then we'll weigh the gum, and this can keep on heating. When you do this in college, you actually will do it very systematically, where you heat it up, weigh it, heat it up, weigh it, heat it up, weigh it, and it takes forever because you have to let it cool and weigh it, let it cool and weigh it. But you have to stop when it has stopped actually gaining weight, because then you know the reaction is complete. It takes forever, so we don't have time to do that. We're just going to do it for a really long time and hope the reaction is complete at the end. And we can compare to the predicted value and see how well we did. It works out well for most years. So, anyhow, as it chugs along there, look at the back of the first page. And it says calculate the expected value for the percent mass of oxygen from the periodic table. So if you look at your periodic table, this is something that I think you'll learn kind of in the next module, but I'll walk you through it once this time here, since you haven't actually learned it in the book yet. The atomic mass of oxygen is the first thing you need to know. And if you look at the periodic table here, actually on your table it might be a little different. Oxygen, on my table it says 15.9994. Your table says 16.0 right there, and we'll go with that. So, it already tells you the answer on your sheet. Look at that. So 16.0 AMU. You get that from the number underneath the letter O on oxygen squared. That means each atom of oxygen has a mass of 16 atomic mass units, AMU. And then the molecular mass of magnesium oxide, what you do there is you take the 24.3 for magnesium and the 16.0 for oxygen, and you add those two numbers together. And you find that one magnesium oxide would be 40.3 atomic mass units. So to find the percent mass of oxygen in magnesium oxide, you just divide oxygen 16 by the whole compound, 40.3. And then you multiply by 100% to get a percentage. So everyone type that into your calculator, 16 divided by 40.3 times 100%, and see what percent by weight of oxygen magnesium oxide is.
Could you repeat that?
It's right on that back page right here.
60.0.
You do this, 16 divided by 40.3 times 100%. And that tells you by weight what percentage of the compound magnesium oxide is oxygen. Like you could figure out what percentage by weight you are of water or of calcium or whatever this is. And what do we get?
40.
39.7%, because we have 3 significant figures.
Ah, he's right. So we have 3 significant figures in each of those numbers, and 100 is perfect. So 39.7%. So if we use a periodic table, which is a reliable source, we would expect to find 39% oxygen-ish. So we'll find what we actually get later and see if that works. So while this is still heating, is the crucible red yet? It doesn't look red on mine. There we go. Now we're moving. Looks like we're losing a little mass to vapors there. All right. So, let's go for the gum mass now. Does your gum feel like it's not sweet anymore?
Yeah.
Gotten all the sugar out? Good. Okay. So everyone with sugar gum, if you have your piece of paper, feel free to spit now. That's what we're going to do right now. We're going to find the mass, hopefully. All right. So spit out gum and space in here. And we know how much our papers all weigh, so we can find the new mass of the gum. So here, aim the camera. Okay, so it's tared to 0. And what do we get? So the sugar gum now has a mass of 14.89 grams. 14.89 grams here. Expand this before I come over into the other side.
Wait, like there. That was the mass of the gum in like the equation.
Not want to drop the lid into the fire. So the gum with the sweetener was 46.94 grams. Now it's 14.89 grams. You can see that bunches of sweetener came out. And you guys can spit. It doesn't matter what paper you take. You can pick one. We'll just weigh them all together. Okay. Mom, feels normal. Oh, nice and scale. Okay, so our mass is chewed up. Did I have everyone's gum? Okay. 7.05 grams. And there is, okay, pile of chewed up gum. Awesome. 7.05 grams. Now, this will just show you how to do the math for percent composition. We'll calculate the percent composition of both here. So, And make sure you've written your procedure steps for that. Like oxygen was fanned, or air was fanned into the crucible periodically. And if it goes wrong, of course, you have to record what actually happens, not what we're hoping will happen. We're still smoldering away in there. Oops, I'm going to break the lid. No. So, what you want to do now for the sugar gum, everyone has the data, so you can do both. You want to take the mass of the gum and the sweetener minus just the mass. Oh, wait. We didn't subtract out the paper from these, so we need to do that. So, our paper on the sugar gum was 1.60 grams. So this would be, really the gum that's left is 13.29 grams. And then here, if we do 7.05 grams minus our paper, which was 1.09 grams, all right, there we go. Now we've got our good data. So, for the sugar gum, the mass of the gum and the sweetener was 46.94 grams. Now we'll subtract the mass of the gum without the sweetener, which is 13.29 grams. And then we'll divide by the mass of the gum and sweetener, the original mass, 46.94 grams. And we multiply by 100%. Now this should look very familiar because it's our percent error equation, but it's also the way you find percent composition. So this will be the percentage of sugar in the gum, because what we're doing here is taking the gum plus the sugar minus the gum without the sugar, so this should give us the mass of the sugar that dissolved away. So when we do that, the significant figures are easy because we got to the hundredths place everywhere. 46.9. How many significant figures should I keep at the end here?
4.
So when I do this top subtraction, here I get 33.65, which still has 4. So I can keep 4 because this is 4, this is 4. When I divide, still 4. So I got, what, 71 point what? Anyone have it? I lost my number. 46.94 minus 13.29 divided by 94. Now, I want everyone to get 71.7 on their calculator. If you can't, I'll help you out. And then once you've gotten it, you can go ahead and I've checked it, you can work on the percent for the artificial sweetener.
I got
1.98.
Me too.
I got
Yeah.
1.927.
You're ahead.
I got 1.98.
Yeah.
Go on down there to the next one.
And then times 100%, that's 198.6.
I don't have my calculator. We're getting
Hold on, that's not what I got.
198.
We're having trouble.
All right, let's look. So, you have it?
No, I did it like 3 times.
Oh, here, so.
That's what I
I did
did.
more than one.
Let's
I
show
did.
me.
Okay.
Matthew, what do you need, buddy?
I know.
Okay, you don't have a lot of bubbles, so.
That's what I got.
The luncheon?
subtracting
Okay, good.
divided by 9.
Oh, that's what it is.
And I got
That's a
198.
46. This is the same number right here. It's just my marker is not showing up as well. as
Oh.
There we
Okay.
go. Yes, it's this number here.
Now I understand.
It does like
That
percent
makes
error.
sense.
Yeah.
It's accepted minus experimental divided by accepted. It's like the same equation. Original minus new divided by original. So
I got 72.7.
I'll come look. Hold on. Let me fan a little. Woo.
There we go.
That makes a lot more sense now.
Way better, huh?
Just to add, technically, doesn't that answer we keep forcing it in figures? It's just 100% perfect, and that all the other numbers have 4 significant figures.
They all have 4, so you can keep. Oh, 4, you're right. Oh my goodness, what is it?
71.68.
6, 8, or
6, 9.
9%. Awesome. Good catch. Okay, what do we get for the percent composition of the artificially sweetened gum?
57.9.
Tell me.
57.9%.
So you get 57.9. Everyone agree with that?
What?
For if
For
you
the
do the
other one we
artificially sweetened gum, so you would do 14.14 minus 5.96, this right here, divided by 14.14 times 100, and you would get, tell me,
57.9.
7.9. Because you have 3 significant.
yes, because you go down to 3 here, so 57.9? 9? Okay. So, what we find is, of the sugar gum, the sweetener is 71.69% of the mass. Of the artificially sweetened gum, the sweetener is only 57.9% of the mass, but it's not really that big a difference. I always thought artificial sweetener was like so much less than sugar, mass-wise, but it's really not that huge of a difference, is it? I thought that was kind of interesting. So you've got percent composition of gum, you know, about how much sugar is in the 2 types of gum. And we looked at significant figures, which is good. Most of you are doing really well with that, though. Oh my goodness gracious, I found my lost magnets. They're in there. They're stuck to the metal plate. I dropped some magnets last year. I guess they fell in my lab bin and stuck to this metal plate, and now they're being roasted.
How long?
Is that a source of error?
I don't think, but I think we might be doing an experiment on the effect of heat on magnets.
It's gonna blow up. Is it? Is it supposed to blow up?
All right, it's probably about time to open a window here just to be on the safe side.
No, that could be
Magnets were dropped into. A magnet was found years ago.
All right. Lucky it's a nice day. Okay, so we've looked at that. We'll have to wait for our data because it's so most definitely going through the reaction. So glowing red and lighting up when I blow on it and add oxygen to it. So we'll have to wait to gather our data for that a little bit. So let's move on and look at these questions. So question 1 here says, the magnesium metal seems to gain weight when heated. State the law of conservation of mass. So what are we going to write for number 1 on the question? The law of conservation of mass says what?
Matter cannot be created or destroyed, but can change form.
Right. Matter cannot be created or destroyed, it can only change form. And you could also state that, chemistry-wise, as every atom that experiences a chemical reaction is still there at the end of the reaction. So every magnesium and every oxygen atom that are reactants are still there as products. So the weight shouldn't change. But we couldn't weigh the oxygen first, so That's kind of the issue. So the magnesium seems to gain weight during this reaction. That obviously is a violation of the law of conservation of mass. So what's really happening?
Oxygen with it.
Oxygen is being added from the air that we couldn't weigh before. So all the extra weight that the magnesium gains is oxygen from the air, because we're making magnesium oxide. So all the mass the magnesium gains is from the oxygen it reacts with. It gets bonded to it. Number 2 says state the law of definite proportions. So this week we talked about the law of multiple proportions. Last week we talked about the law of definite proportions. So you can state that as a happy little definition from your book.
Are we doing this all right now, or?
Yeah, we'll go through the questions now, because the heating takes forever anyway. The proportions of the elements in a compound are the same. That's what I have written here. That's not the greatest. Let's do better. I don't love that. The law of definite proportions. The proportion of elements in a compound is always the same. There's a recipe for every compound. That's kind of the way I like to think of the law of definite proportions.
What
A
is it again?
fixed recipe for every compound.
What is it again?
It says here, the proportion of elements in a compound is always the same. But I like to think of it more as there's a fixed recipe for every compound. So, number 2 also says, what is the proportion of magnesium to oxygen in MgO? So if we look at the chemical formula for magnesium oxide, it's MgO. So how many magnesium atoms are in that?
1.
And how many oxygen atoms?
1.
So the proportion of magnesium atoms to oxygen atoms in magnesium oxide is?
1 to 1.
1 to 1. Then, how about by mass? So we did that up here. By mass, we would expect magnesium. Let's see, the mass of magnesium on a periodic table is 24.3. And you guys haven't learned what AMU is, but it's atomic mass unit. It's like gram or pound or something. But, well, pound isn't a mass unit. Slug, I guess. It's a mass unit. It's a very tiny mass unit for measuring the mass of an atom. And oxygen has a mass of 16 AMU. So our proportion by mass would be 24.3 to 16.0. So, assuming that we have sources of error that are obvious when I weigh this, I don't know how we're going to do. Some music goes really well. Well, I think it's done. What kind of sources of error might we expect from this experiment? I don't think they'll hurt anything.
Should we mention it though?
No. They're in there. They are. I found them. Finally. Later. Okay, it can cool off right there. Did you all see the kind of vapors wafting when I removed the lid sometimes? So I think we're losing a little bit of mass just from that updraft from the heat. That's the source of error. The biggest source of error in this experiment, though, is sometimes, like when I burned this piece of magnesium here for you to see it happen, you can see, like if I sift through, right here, see there's little flecks of magnesium that just got coated in magnesium oxide but didn't actually react because they were coated, no oxygen could actually get to them. So that's kind of the big source of error, is some magnesium metal didn't get to oxygen to react. So it just remained magnesium metal, and it didn't form magnesium oxide. So if all of our metal didn't react, that's our biggest source of error. Hopefully I heated it long enough and added enough oxygen by fanning it to get it to all react, but chances are good that some of it got surrounded by magnesium oxide and some of the metal didn't actually get some oxygen to react with. So that happened. And we can poke through it after we weigh it and see how much we think that happened. But we got to get it smashed first before we spill any.
Is that still in the procedure, or is that part of
That's part of the error. Really, the procedure was just, it was heated until it seemed to stop reacting. Fanned occasionally. I mean, it's pretty simple procedure. Packed in there, heated, fanned. When it stopped reacting, we stopped messing with it. But don't say we. It's a rate for procedure in third person past tense passive voice. All right, so some sources of error would be it didn't all react, the metals didn't all react, and probably a little bit of mass was lost in the updraft of the vapors. So number 4 says, is MgO an element or a compound?
Compound.
It's a compound. Magnesium is an element, oxygen is an element, but magnesium oxide is a compound. 2 elements chemically bonded together. So our data here, 13.2 grams is the end of the sweetened gum, and the artificial gum is 5.96 grams. And that's the first percent composition of the gum. All right. If I find my metal scale, I might be able to get the mass here. Not screaming out anymore. All right. Moment of truth. Did it work? Well. Okay. So now the crucible lid and the contents, I dropped it on there. Awesome. Let's try that again. Okay, so the mass is 22.2 grams. So I might erase this. All right, MgO is a compound, 22 point. All right. So if we subtract the mass of the crucible and the lid, then we can find just the mass of the magnesium oxide. Is that right?
Would it be 1.2?
1.24 grams.
Don't go to the base of least significant.
Well, but my scale goes up to the 100th place in both, so we're okay. Okay, so now we have some data to work with. We can back up a little bit. Maybe we'll finish number 4. Is Mg an element or a compound? Mg is an element. So magnesium oxide, MgO, is a compound, but Mg, just magnesium metal, is an element. Anything that's actually found on the periodic table, just like that, like Mg or O, is an element. But the 2 chemically bonded together are a compound. So let's head back to kind of the top of the back page there. And no wait, the bottom of the front page. You should have everything filled in up to the mass of the MgO, which is right here. So we're on that kind of last blank on the page. Experimental percent oxygen by mass of MgO. So we take our mass of magnesium oxide, which is 1.24 grams. We subtract the mass of just the magnesium, which is 0.81 grams. Then we divide by the mass of the magnesium oxide, 1.24 grams. Multiply by 100%. And then we have to think about significant figures, especially because when you add and subtract, then you have to round, and then you'll end up with, I don't know, 2, hopefully, maybe 1, if we're unlucky. That has happened in this experiment. Use a calculator for me. Everyone can take off your goggles, too. See? If you guys want to pass the bag around, everyone can put them in. All right. Much better. So, does anyone have an answer for the percent oxygen in magnesium oxide?
34.7%, because we have 3 significant figures and all numbers.
But here, when we do this subtraction, we get 0.43 grams, and that's going to be 2.
Okay.
So we're going to have to round it to 2.
In that case, it would be 35%.
Divided by 1.24. Yeah, 34.6, so we have to round it to 2, so we'll get. So, we think 35% oxygen there. How close are we to what we expected from the periodic table?
We appear to be off by,
That's
I'd say
not
about
terrible, is it?
4.7%.
And we can find my percent error by taking the 39.7% that the periodic table tells us we should have gotten, and subtract our answer, 35%, divide by what we know should be true. This is our percent error, which is just like percent composition, which we'll do lots of times all year. So. And I get, looks like 12%. I said if I'm under 10%, that's good, but I'm okay with 12, really. That's pretty good. And then we could, let's see if I have another little tissue in here. Yep, I do. So, now that we've gotten the mass and we don't need this anymore, I'll pour out the contents and we can have a look to see why we've got so much error. My guess is that about 12% of my metal didn't react because it got coated. And you can see there's kind of a little core of metal in there, right in there, that didn't get reacted. It's right here. There's a little piece. If it crumbles, it probably all reacted. But then these pieces right here, is the camera running? There are some pieces of metal. Okay. There are some pieces of metal that didn't react and aren't that crumbly, that were kind of on the edges or in the center, like that right there.
From the camera's point of view, it's so fuzzy.
Like this chunk right here, I can't crush, so it didn't get reacted, I think. This, everything, oops, sorry. It very safe magnesium oxide. Now that it's not hot, of course. So, there are definitely some little chunks of metal right there that didn't react. And that's where most of our error is coming from, I think. And the fact that our percent oxygen is smaller than it should have been means that those bits of metal didn't actually react. This is gonna be awesome.
Sorry.
Okay, so now to learn the stuff that's really critical for test taking and making it through the rest of the year in chemistry. How do we name compounds? So let's look at the very bottom where it says nomenclature, part 3 on the back of that worksheet. Binary ionic compounds. So binary, what does bi mean? 2. So binary ionic compounds contain how many different elements? 2 different elements. They contain, so if they're ionic, they have one what and one what? One metal, one non-metal. They might contain 2 atoms total or more than 2 atoms total. So magnesium oxide has 2 atoms in it. If we, for example, let's see, let me think of, I can't really think of an ionic that's super familiar to you guys that would, well, we could say magnesium chloride. You don't know how to do yet, but magnesium chloride would have this for its chemical formula. So how many atoms does it have in all? 3. 1 magnesium plus 2 chlorines gives us 3 atoms in all, but it's still a binary ionic compound because it has 2 types of elements, magnesium and chlorine. So may have 2 atoms like magnesium oxide or more than 2 like magnesium chloride. And soon you'll know how to write magnesium chloride just from looking at the periodic table. Maybe really soon, actually. So if you look at the last page here on number 2, a blank compound contains 2 atoms. They may or may not be the same 2 elements. What kind of compound has 2 atoms? I guess it's binary. What am I going for there? I don't know the answer. What kind of compound has 2 atoms? Oh, I know! I know the answer. Hooray. Anyone else? Another prefix that means 2. Di. So a diatomic compound contains 2 atoms. And you guys are going to be memorizing, this is the word right here, diatomic. A diatomic compound contains 2 atoms. You all are going to memorize 8 homonuclear diatomics this coming week. Hydrogen, and then 7 more that actually make a little shape like a 7 on the periodic table. Walk off like a 7 right now. This group of 7 right here.
Is that written down somewhere?
Yeah, it's in your book, and it tells you to memorize it and what you're going to read this week. So hydrogen, and then the 7 here that make a 7. And they only exist in nature in their elemental form as diatomics, H2. That's a homonuclear, meaning 1 type of nucleus, hydrogen. Diatomic, meaning 2 atoms bonded together. So you never just have an H floating around in the air. H's don't exist all by themselves. They always combine with another H to form hydrogen, H2. All of these guys, N2, O2, F2, that's how they exist in nature. They don't just sit around all by themselves. So diatomic compounds have 2 atoms. And your book will tell you to memorize those 8. Then it says, when naming binary ionic compounds, always name the metal first, and then the non-metal. And you put the IDE ending on the non-metal. So, for example, the one we've been working with today, magnesium oxide. With ionics, you just say the metal's name just like it is. You don't have to change it at all. Magnesium, just like it is on the periodic table. And then the non-metal, when it's just a binary compound, oxygen. So if I write the word oxygen, then I have to take off the ending here and add that IDE ending, oxide. And you'll get used to doing it. So
How do you know what's the end there?
Oxygen always turns into oxide. Everything else is kind of easier. Hydride is hydrogen. So here, for example, we have chlorine. So most of them have an obvious place where you change the ending to "ide." So chlorine, chloride, that IDE goes like that. Fluoride, bromide, sulfide. And you'll get used to it because we'll do, in just a moment, like 8,000 of these. And then it'll be easy, second nature for you. But you're going to add that IGE ending to the non-metals for ionics. All right. Any questions so far? Okay. With ionics, you never use those prefixes that you all learned in your reading this week. Those are only for covalent, all non-metals. Ionics don't use any prefixes either. So, gather in groups of 2 or 3 and try to name those guys in number 3. And then we'll go over them. You can stop filming while we boringly